Well, good afternoon, everyone. And I'm very glad to participate with you in this, what you call Congress and I call conference. I have actually been to your university, to the university before, and participated in giving a couple of courses over the years, because I've been going to Lima to Peru for the last 18 years or so, working on several mining projects. But as you notice from the date since my graduation, I'm getting a little older, and therefore I'm resigning from most of that work. So getting up to elevation 14,000 is not as easy as it used to be.
14,000 pies no es tan...
Elevation 7,000 feet, which is roughly what, 2,300 meters.
1,300 metros de altura, pero ir hasta 48,000 como las Bambas, sí, es muy difícil. Entonces, les deseo a todos un buen día y espero que disfruten lo que se ha presentado hasta ahora. El tema que voy a referirme ahora es sobre la liquefacción. Y dando el tiempo limitado que tengo de 45 a 50 minutos, no podré debatir a mayor detalle, pero voy a tratar de cubrir ciertos puntos importantes, ciertos puntos de importancia. Y espero que tengamos tiempo al final para que ustedes hagan todas las preguntas que les guste, que puedan tener. Voy a referirme al estatus actual para evaluar las consecuencias desencadenantes y las mitigaciones, y cómo funciona la mitigación aplicada y razonablemente para proyectos de buena dimensión y en Canadá. Ok, entonces avancemos. La liquefacción ha sido observada en mucha parte del mundo durante siglos. Prácticamente no se le prestó atención por la profesión de ingeniería hasta la falla de la presa de Fort Peck en el año 38. Fue una liquefacción estática de un relleno hidráulico, pero incluso entonces no se prestó mucha atención. El profesor Casagrande pasó tiempo estudiando esto y luego dijeron, sí, son fallas hidráulicas, pero lo siguen utilizando. Pero luego, cuando se dio el terremoto en Alaska y de Niigata en el año 64, comenzamos a prestar más atención y nunca hemos parado. En realidad, hemos incrementado las actividades. Entonces, ¿cuáles son las consecuencias que hemos observado de los terremotos anteriores? Lo que hemos observado es la ocurrencia de sedimentaciones que pueden ser uniformes en algunos casos, como en Cove, en Port Island, pero pueden ser muy abruptos, muy agudos, una distancia corta. Entonces, no pueden usarse con elementos así de sedimentación. Hay que tener cuidado cuando hablamos de sedimentación. También ha habido pérdida de soporte lateral, donde los pilotes se extienden a través de la capa de suelo liquefado, y también hay flotación de estructuras enterradas debido a las presiones y también a los soportes, la pérdida de soporte de amortiguamiento y otras mayores presiones laterales, con también movimientos laterales limitados o donde el flujo es extensivo en los movimientos.
So let's take a look just very quickly at some examples. I'm sure many of you have seen, if not everyone, I'm going to show from these examples, at least several of them. But this is liquefaction actually in progress. This was taken by someone walking by in 1978 in northern Japan. And he saw this soil and water bubbling, so he took a photo. And there is the effect of liquefaction. And you notice that accompanying that was some settlements of the ground as well, which sometimes can look like this. That's what I was talking about when I said the settlement most of the time is very sharp, not nice and uniform. It's very uniform in here, but it's very sharp at this end. So if you had a building sitting on top of that, it could have some serious difficulties here. Or it could modulate some of it, who knows? And of course, this is the famous one. I'm sure if you haven't seen this before, you haven't been working in the area of earthquake engineering. But this was in Niigata, where the buildings fell over because the piles extended right into the liquefied zone, not beyond it, so that the piles broke and the building tilted. It tilted about 80 degrees, so it's almost sitting on its side. But the buildings are so well constructed that nothing broke, there was no collapse of the structure itself. It's just this foundation that looks like great. And people were able to get out of the building, I'm sure in a very difficult way, climbing out of these windows. And this is the example of the flotation of tanks due to increased bore pressures and the uplift caused by that. Oops. As another one from Niigata, where there was some lateral spread, a small amount of movement of the embankments of the river, causing the separation of the bridge and the falling of the spans of the bridge, rendering the bridge, of course, useless. And you can see there's some major some difficulties here as well. This is the case of the San Fernando Dam in 1971. San Fernando earthquake. I'm showing, this is the dam, the lower San Fernando Dam, and showing where all the population that lived downstream of that dam. And you notice there are two towers there, intake and outlet towers. And you'll notice a little later that this tower has disappeared, but this was still in place even right after the earthquake. This is what it looked like before the earthquake. I'm not sure whether this was taken a year or two before the earthquake occurred. So it's 1969 or 1970. The earthquake occurred on February 9, 1971. And this is what that dam looked like shortly after the earthquake. You can see that this was the crest of the dam. It's no longer way up on top. And fortunately, the reservoir had been emptied about a year or more earlier to evaluate the ability of this dam to withstand earthquakes. And it had been approved to refill about, I think, October or November of 1970. It was the water was on its way up, but it had not reached the allowable level. And that's why you have a little bit of freeboard still left, even after the failure of that. I mentioned something about the intake outlet towers. The one that was in the middle is gone. Remember that one right here? That's gone. But the other one near the right abutment is still in place. And that was very fortunate because they were able to immediately start emptying the reservoir and avoid having this part erode and cause a spilling and basically eroding the entire dam and maybe really harming all these people. In fact, they did tell people to evacuate. About 80,000 people evacuated their homes downstream of the dam. And this is what it finally, the upstream part looked like. This is that tower. And shortly after the reservoir was emptied, this tower fell over, I think, due to wind. And this is what happened in Kobe. This is a separation. This is the port part of the port island, causing these lateral deformations and caused a lot of damage to the many structures. So how is liquefaction triggered? Of course, we see it happen in the field, but we don't know what is going on in the field, so we have to study it in the laboratory. And it's been studied, among other places, both using drained and undrained testing apparatus. In the drained conditions, this work was done in 1972 by Yao. He just ran a test. It was a dry sand, but it still shows what happens as you vibrate the material. And he's looking at the void ratio as a function of how much displacement there was taking place in the specimen. And it started at point A, it densified by decreasing the void ratio. And then shortly after that, started expanding or dilating as the shaking went on. But then it became looser than it was originally. And then as shaking continued, it began to decrease in volume and then went up a little bit, but as just on and on and on, it ended up with a significant amount of reducing the volume. So then the net effect, if you have drain conditions and you apply a cyclic loading to a soil, it will eventually compress or decrease in volume. So when you apply an undrained, under undrained conditions in a laboratory, which correspond more to what happens in the field, because most these liquefiable soils are permeable, but not that permeable, and the shaking takes place only a few seconds. Therefore, there's no ability to actually consolidate or to decrease in volume the way the material wants to do. So going back to the laboratory for a cyclic undrained test, starting at point A, and as the cycling was going on, the soil actually wanted to go along this line to compress down this amount due to the shaking, but it couldn't do that because it's undrained. Therefore, it has to stay at the same void ratio. And therefore, the skeleton had to give up some of this effective stress that was being applied to it and transfer that to the water, which became the excess pore water pressure. And the effective stress was decreasing from this value down to this value. And of course, if this can continue on, it could actually decrease to practically zero, or the pore pressure being equal to the initial effective stress. And then, then basically when you run the full test and examine everything that's happening in that test, here's one where this is an undrained cyclic triaxial loading test done on Sacramento River sand, where you apply a uniform cyclic shear stress, and you measure the pore pressure being generated as shaking goes on. And this value RU is really an expression of the ratio, of the whatever the excess pore water pressure is divided by the initial effective stress. So RU of 0 means that there is no excess pore pressure, and RU of 1 means the excess pore pressure has equaled the confining stress. So in the test, as that being monitored and now expressed in this value, it reaches 1, but it sort of oscillates up and down around 1 as the shaking went on. But while that's happening, there's straining is also taking place in the sample, and it initially begins very small, but then starts growing and reaches some value, in this particular case, about 2.5%. So then what do we do? How do we define a state of liquefaction? In the field, we only see that there is something happening, like we saw the settlement, the cracking, the lateral movement, what have you. But in the laboratory, we have these things that we can measure, the pore pressure and the displacement. Therefore, the criteria for deciding what goes to triggering is, in the laboratory, can be reaching a pore pressure U equal to the initial effective stress. And then expressed in terms of RU, it's the ratio of U over sigma prime. And when it reaches 1, that's 100% pore pressure ratio. But in most cases, as we saw in that lab test, it really actually touches 1, but then comes down below that as shaking goes on. So it's a little bit less than 1. Or because sometimes we can't really measure pore pressure that well, or pore pressure is not as uniform as it could be in the sample, it's much easier to define things by something we can measure a little more precisely, which is a strain. And so we use the double amplitude strain, and in triaxial test, we use something like 2.5%, and in the direct simple shear test, we use about 3%. Of course, in that field, we can only look at what is the evidence of liquefaction, the cracks, the ejecta, soil spurting out of the ground, lateral movement, and so on and so forth. That's where we are with respect to that. So now, how do we evaluate that? Since it is of concern to us, we've seen some difficulties with it. How do we evaluate that? And the approaches that are available to us really are three. We can use what we call the stress approach, the strain approach, or the energy approach. These have been all developed, proposed, and attempted to be used. And what we've discovered is the simplest one to use is the stress approach. The strain approach is probably the most fundamental one, but it's a little hard to use. And the energy approach is a very appealing one, and several people have attempted to do it. And I'm sure there will be more. But its application is not that easy to do. So in essence, then we basically have all stuck to the stress approach. And the stress approach is very simple. It consists of comparing the capacity to demand. And capacity is the stress required to trigger liquefaction. And we typically take whatever that stress is and divide it by the initial effective stress. And we call that the cyclic resistance ratio, or the capacity expressed as a CRR, cyclic resistance ratio. And we can get that from the laboratory, or we can do it by back calculating case histories, which I will mention again, but I will not describe how we do that because there's just not enough time today. And then the other side of the equation, which is the demand, is the stress induced by the earthquake ground motions. And again, we normalize that with the effective stress at that particular depth we're looking at. And we call that the cyclic stress ratio, which is the demand. And we can get that from a site response analysis, or we can get that using a simplified procedure, which I will not describe, I will just mention again. So the CSR, that's the stress induced by the ground shaking. From the site response analysis, we get a tau max, and therefore we have a maximum cyclic stress ratio, and we normalize it with respect to the effective stress at that particular depth where we're calculating that stress. Or we're using the C. Idriss simplified liquefaction procedure, which we developed back in 1969, 1970, and was published in ASCE in 1971, using this very simple equation, which I will describe shortly. And these are the definition of these various symbols. Now, by the way, I can send you a PDF of this file if you want to distribute it to the attendees. Would that be a good thing to do? Hello?
Yeah, Professor.
I can do that actually. Maybe you can communicate later as to where I should send it, but I'd be very happy to do that. That way they can go back and look at if you forgot something I said or something like that.
Thank you very much.
Now, the basis of the simplified equation that I just mentioned is actually Newton's second law, F equals to ma. So tau max is equal to M is the weight of the soil, or the total stress at that particular depth, and A is
es la aceleración superficial. Eso que llamamos. Pero eso resuelve en la curva que está, como es una curva de color negro así. Que asume que nada está cambiando en la profundidad, que la aceleración es constante en la profundidad y por tanto la fuerza inicial va incrementándose al incrementarse el peso o su masa. Pero en la realidad el suelo no se reduce.
And therefore we created this ratio of what it should be, which is the blue line, divided by what we calculate as a rigid body, which is the tau max R, and we call that a ratio tau max D for the soil, or deformed soil, or the non-rigid soil. And divided by that, we calculate using this very simple equation, and we call that R sub D. And the nice thing about this is the ratio of stresses. And stresses always behave in this fashion when you calculate them. And they might oscillate a little bit. They might exceed this value slightly near really at this depth. And most of that is because of the inaccuracies of computation, not it's minor variations there, but invariably they always are decreasing in this way. So that ratio is always starting near 1 or at 1 at the ground surface, and is always decreasing with depth. Now, while I'm at this, talking about this, it's really useful to say why we keep using acceleration as the basis. I know you've all read, and I don't know how many of you have not, all read about how beautiful it is to use areas intensity instead of acceleration, or the absolute maximum absolute CAV, absolute velocity, and or some other parameter. The only problem with that is we typically have an idea of what that value is at that depth, but we need it at some other depth. Just like the stress, we calculate it over here at this depth, and we know how it varies. Therefore, since we can calculate it using this equation, guesstimate it initially using this equation, we can modify it by a ratio that we know is always less than 1 and get something comparable to what might be closely correct. But if you're using areas intensity, and areas intensity is a function of a squared, the acceleration squared with the acceleration oscillates all over the place. If when we make calculations, that's the only time we know that. We do have a few downhole arrays that tell us something about that. But they oscillate all over the place, and that ratio would be oscillating all over the place, and we don't know how we can use it for forward calculation. We even use it for case histories. The same thing applies to CAV, or the absolute velocity. And therefore, I think we're stuck with stresses for a long time to come. And this is how this R sub D varies with depth. I don't want to go. Now, the other thing we also need to worry about is can we get rid of that thing at the top? Can you can see the entire slide. There's no, and on mine it's covered by whatever Zoom covers it with.
I can see your full screen.
You can see the top effective duration or something?
Yes, sir. The title is effects of duration, yes.
Okay, so it's just on my computer that is doing this to me. That's okay. I don't need to see that one. I'll be sure the listeners can see it. But anyway, the duration is also an important issue, and we need to take care of that, because earthquakes, first of all, we are making sometimes comparison between what we calculate using earthquake ground motions that are non-uniform. I'll show you an example of that shortly. And lab data, which are usually done by using very uniform shear stress like this. So we need to find a way to go from one to the other. And so if we look at the lab test and we run a test like the one I showed you before, and out of that, we get that this reaches 100% pore pressure ratio, or a certain strain level at something like about 2060, 26 or 27 cycles. And the applied stress was about 0.332, something like that. So we can plot a point on a cyclic stress ratio versus number of cycles, a point like this one. And we can run several other tests and eventually get a plot that looks something like this. So now we know how things go as a function of duration when the imposed load is a nice uniform load. But then how do we translate that to the effect of earthquakes? There are ways to do that. I will not have time to really go through that tonight, but there are ways to do that. And as a result, then we can take a time history, which is what an earthquake would cause. And there's a huge difference between how long the shaking goes on if the magnitude is like 5 or 6 or 7. You can see how different it is. This is like about 2 seconds, this is like about 7 or 8 seconds, about 20 or so seconds. They're not of equal amplitude either. So you have to find a way to change to some equivalent nice uniform amplitude. And there are other things that affect how we approach this. And these are, as I said here, confining stress, initial shear stress. But I won't have time today to really go through all of that. And if you want to dig into the details, at least I'll show you at least two references you can go to. One is the monograph that Professor Boulanger and I wrote 14 years ago now, but it shows the details haven't changed. And you can go there, you can go to the Earthquake Engineering Research Institute. I think you can get a electronic copy of this monograph for either $15 or something like that. It's not a very expensive one. And then the other report, which updates some of the stuff that's in the monograph for the CPT and SPT, again by Professor Boulanger and myself. This was published as part of the Department of Civil Engineering at the University of California at Davis. So if you can get to that website, you can go to the publications and you can access this and download it for free. It's a very easy thing to get. So now, based on all of that, as I said earlier, hello? Somebody? Oh.
Working on that.
Somebody's in my iPhone speaking to me. Anyway, as I said before, we can get, use case histories to develop the procedure to evaluate the triggering of liquefaction. And to do that, then we need a parameter to use to correlate among the various cases. And we can base that on laboratory tests or on some field measurements, in situ measurements like SPT or CPT or shear wave velocities and so on and so forth. So then I'm just going to mention what these field-based case approaches are. They are SPT, CPT, and VS. And these are described in many publications. I just will not be, again, able to describe them. But if there are any specific questions, I'll be happy to answer that when we complete this presentation. There are other people now are beginning, well, they have been for the last 10 or so years, like the dilatometer and what have you. But the way this thing evolved actually is very important. We started out with the SPT. In fact, actually, the first attempt back in 1967 or 68 was using the relative density, which is a very crude way to do business. We shifted to that SPT in the mid-70s. And we had actual measurements of SPT values at those where the case histories were observed, in Niigata, in Imperial Valley, and a few other places. Then we began to say, well, but CPT is a very valuable tool we can use. It has a lot of advantages over SPT. It has a few minor disadvantages, but it has a lot of advantages. So we started initially back in the early 80s. In fact, Professor Seed and the late Professor Seed and I published a paper on that in 1981, correlating the two by finding a ratio between Q, which is the tip resistance of CPT, divided by N, which is the blow count from SPT. And it was very crude, and it really was not particularly valuable, except it opened the door. But what it forced us to do was to go back to all those sites where we had observed, but did not observe liquefaction, and get the CPT data directly at those sites. And since that has happened, and in the last 20 or so years, we have tremendously improved the CPT. In fact, I used to think only SPT should be used by itself. Now I believe you can use either one by itself as long as you get some samples of the CPT. So as far as I'm concerned, actually, I give preference to the CPT. And I always like to try to get a CPT at a particular site and then decide where I need some samples to be sure that I get the right fines content, or if there's any plasticity, I can measure the Atterberg limits and so on and so forth. The VS-based has also been based on, in many cases, on actual measurements at those sites. So it's, from that point of view, it's very useful. The only thing is, VS is not as dependent on how dense the material is. And therefore, you see the relationship is so tight that a small inaccuracy in measuring VS can lead to a huge difference in your conclusion when you use that procedure. So I don't object to its use, but please, if you ever use VS-based, use another procedure at the same time to be sure that you're reaching the same conclusion. Now, one of the difficulties we're having now with SPT is that we only have data, we only have cases to the extent of maybe about 15, 18 meters, roughly. What's that? About 50 to 60 feet, roughly. And when you get below that, we're finding that the CPT, let me back off a little bit. The CPT and the SPT seem to give about the same conclusion at shallower depths, like 10 meters, 5 meters, 15 meters, where we have all the case histories, because we based both the procedures been well done up to now. And but as you go deeper, what might be happening is that the CPT does not have any depth limitations in terms of the effect of how you get the tip resistance and since we correct for effective confinement. But the SPT, since we're basing it on a given energy level that we are applying to as we drive the sample, the N60, as we all call it, or assuming that, or hopefully measuring that we are getting 60% or whatever number we're getting at the drive head. That's where we measure the energy. But as you go deeper, actually things could be losing energy a lot more than that. And as a result, we might be, by the time we apply any correction, we're making the material a lot denser than it really is. And as a result, you get some difficulties. So I would tend not to apply the SPT below about 15 or 20 meters at the most. So I just want to tell you that to keep that in mind. And then these are described in various publications, and I'm not going to see much about them. Now, what's been also happening, as I said before, that things we have never stopped. We started back in the mid-60s and kept on and on and on, and we've never stopped. There used to be 2 or 3 or 4 people working on the subject. Now there are about hundreds of people working on it, maybe thousands if you look at the entire world. But what's been happening in the last few years is there's been a comprehensive program to collect, examine, archive, and use liquefaction, no liquefaction case histories, including all the ones we've been using up to date, augmented by the more recent ones that came along with the more recent earthquakes, and some cases that we had not collected before, and going back to some cases that we had collected and re-examining the data and maybe making some modifications. It's very similar to what was happening with the earthquake ground motion. That was called the New Generation Attenuation Project, NGA. So the liquefaction people got together and said, well, let's imitate those guys and start an NGL, New Generation Liquefaction. And that's what's been going on. And they just decide, some developers, I think 4 or 5 teams now are starting to work on developing re-looking at the data, examining everything, and updating these field-based liquefaction evaluation procedures. They're all talking about using areas intensity, accelerate, CAV, absolute velocity, and various other parameters. And I'm sure they'll also look at acceleration as well. And we hope that something will be coming out late this year, possibly as late as late next year. But please stay tuned. That's a very important development going on. And hopefully we keep improving things as time goes on. So then having had a problem, if we determine that we have a problem, what can we do about it? There are various options that we can look at. If we have identified a liquefaction issue at a particular site, just accept the risk and do nothing. We've done that in the past quite often. And we can design for the consequences, like if we expect settlement and like that building in Niagara, had they driven the piles another 10 meters or so, they probably would not have had any problems. But that's designing for it. And we can take out the material and replace the vulnerable soils, remove and replace with the improved soils. We can improve the ground in place, and we'll talk about that a little bit. Or we can have a combination of these. And one part we'll do this, one other part we'll do that. So that's really what's available to us. Now, looking a little bit at this ground improvement, which has become a very important topic and is really being invoked on many sites throughout the world. There are many existing dams, embankment dams, certainly in the United States, and I know in Latin America, including Peru, where the foundation was not as good as it needs to be. When the dam was built, you had to go back and improve things. Or the material that was put in place, like a hydraulic fill. There's still many hydraulic fill dams in the US, and they need to be improved. So anyway, ground improvement has become a very important topic. And these are some procedures that are available. The deep dynamic compaction. And for deep dynamic compaction, please keep in mind, no matter what the contractor tells you, that it's not good beyond about 10 meters. It's just totally ineffective. They say, we'll triple the weight, still does not improve things beyond about 10 meter depth. So keep that in mind if you ever use it. As a vibroflotation, there's stone columns. Stone columns have some problems, but we're not going to talk about the advantages, disadvantages, just to list them right now. Deep soil mixing, compaction grouting, blasting, in-ground walls, and so on and so forth. Quite a few procedures. And Professor Mitchell, who is our guru on ground improvement, has been since maybe the last 40 plus years, put together this chart. Oh, this is something, unfortunately, the title of the figure got double jammed, so to speak. Let me see if I can correct that. There we go. And we can go back, and this now can be read, which shows what procedure is most applicable to what size, depending on the soils that are to be improved, ranging from gravels all the way to clay. Of course, for liquefaction, we're really interested in this range that is shown by these two lines. Clay can lose strength during shaking, but it's not a liquefaction issue as the way it occurs in sand, as we've discussed in many occasions before. And silts, as long as it is cohesionless, it can liquefy in a way similar to sand. So these are the various ways, like, for example, deep dynamic compaction is good for gravels all the way down to silts, maybe. Explosive compaction, again, good for these soils. Some are not that great for gravels, vibratory probes. You just can't compact gravels that way, and vibro replacement cannot do that. Anyway, so this is a very useful chart to look at when you're deciding on what to do. This chart was also published in our monograph, so you can see it there and describe it in a little more detail. So I thought I will end my presentation this afternoon by showing you an example where a combination of those ground improvement procedures were used. It is an existing dam in Canada. It's called the Seymour Dam. It's not a very large dam. It consists of an embankment part and a concrete part in here. And the embankment was sitting on a liquefiable soil. And there's no way to save that dam by improving the foundation below the dam. It'd just be too expensive. So what was looked at was, here's the existing dam shown in yellow, and these foundation layers here are, I'll describe them shortly, they're about 30 meters of vulnerable soils. But the idea was to come in and keep the dam exactly where it is, improve the foundation down to 30 meters, and build a downstream new dam sitting on the new foundation, the improved foundation. Oops, I better change back to, here we go, the laser pointer. So that when the earthquake occurs, not if, when the earthquake occurs, Vancouver is in a very high seismic area, the upstream part of the dam will fail, but what's retained after that will be a well-behaved dam. It won't look pretty, but it will not allow the water to overwhelm the city. The concrete part was much easier to improve in place. There were a lot of tendons and various other things. So structural engineers working with us on that, and that was done very nicely. So then looking at that 30 meters of the foundation, it looks something like this. They're all mostly cohesionless. They're all vulnerable to liquefaction. There are a lot of large boulders in this part in here, therefore it could not really be improved in situ. So they decided that the upper 10 meters will be removed and take out the huge boulders, put them aside, or put them maybe in windrow or whatever solution might come up that way, and then put them back in again, properly compacted. The next 10 meters, well, now we're getting into water and therefore can't really excavate very effectively or very cost effectively, I should say. And so you'd be using dynamic compaction. And the deepest part, since dynamic compaction can only go about 10 meters, and we just cannot reach this part using dynamic compaction, was to use blasting in this part. So the sequence of events was to take this 10 meters out, do the blasting, come back and do the dynamic compaction, replace all these soils, build the embankment. That's how the things were done. So that's this is what it's going to end up looking like, and it ended up looking like. Actually, the project was started in the early 2000s, was finished about 2009 or 2010. It took several years to finish, but it was finished. And so that's again describing what happened with the sequence of things: remove and stockpile, use blasting, dynamic compaction, and then put back the soil to get back to where you want to be. So this is the area that's the embankment over here in the upstream side, the water side. And this is the part that's going to be first taking out the first 10 meters, then blasting the lower 10 meters, the lowest 10 meters, and so on. And this was designated in panels, from panel 1 to panel 15 over here. It turned out that the loosest area was here, which we'll see a little later. And then And there were 3 passes. We put them at various depths and various spacing and all kinds of things. We had some fantastic experts in blasting working on this, and Professor Mitchell, Jim Mitchell, the one who showed you that chart, was an advisor on this project. I personally was a member of the technical review board. I was the chairman of the technical review board for this. We had 2 other geotechnical engineers and 1 structural engineer for the structural part. This is just things in progress. Is the drill rig drilling down and placing the material to be blasted. And so a close-up of that machine doing that. And then back to then, I think we're going to look at panel 4 now when they actually blasted it. Here's the blasting in panel 4. And this is what we observed when the blasting took place. You'll see that there is a fountain. It's like the one in Geneva. If any of you have been to Geneva, all the water spurting out in the lake. And a close-up of those 2 is, this is almost a little dirty water. This is very dirty water, depending apparently what it's going through. But it's rising up several, I think about maybe 2 or 3 meters. So it's pretty high. And it just reminds us of what we saw during the earthquake. So the liquefaction was taking place. And as a result of that liquefaction, and then the dissipation, creating high pore pressure, dissipation resulted in settlement. And that's how we measured the effectiveness of blasting. This is one where it really went up. It's about 5 meters, maybe 3 meters, maybe 4 meters. I forget the exact number. We're all standing on the crest of the existing dam, and I took all these pictures myself. So it was fun. It was a very nice day, actually. And this is how muddy and watery it got because of all that water spurting out. So it was very effective. So when you look at this area, these various and the measurement, the pass 1 resulted in settlements up to about maybe 400 millimeters. Blast, and that zone that I said was appeared to be the loosest, panels 9A, B, and C, and 10, I believe. You know, the panels around 9, centered around 9C. And then the second pass, there was an increase, more settlement, but not as much as the first settlements. But in this area, they went up to almost 1 meter. And then the third pass, the third pass is still some more settlements, some a little larger than before, but some a little smaller, and going up to about 1.5 meters. So based on that, we judged that the area has settled enough that it really compacted and made it non-vulnerable to liquefaction in case when the earthquake happens. And then following that, the dynamic compaction, here's the crane carrying the weight, and the weight having dropped and created these craters in the usual way that this is done. Another part. This is that concrete part. This is the existing, the old embankment part. They built a concrete wing wall to create an abutment, since there's no abutment on this side. There was an abutment on the right side, but on the left side, there's no abutment. So, and finally, I have that's really the end of my presentation tonight. It's almost 6:05, perfect. So we got plenty of time for questions. And just a final thought that I thought I would say, rather than giving any conclusion, I basically, if I give you a conclusion, it would be a summary of all the things I said. So there's no point in doing that at this juncture. But I think there's been a lot of things happening in this century, since the beginning of this century, and especially in improving in the analytical and the experimental capabilities. The number of improved constitutive models that have come up and for nonlinear analyses, the improvement in the platforms to run these analyses, whether it is FLAC or Plaxis or hopefully or OpenSeas, so we got finite elements and finite differences. There have been tremendous improvements in that. There have been tremendous improvements in the experimental capabilities, whether it's the huge centrifuge at University of California at Davis, the large shaking table at San Diego, the large shaking table in even Reno, I think, has one now, and it's a huge shaking table in Japan. All of that's being used and providing some wonderful data. And have increased these improvements have increased our capabilities to both evaluate conditions involving liquefaction and to provide increased confidence in our ability to come up with solutions that can be implemented in cost-effective ways. So I have a great deal of optimism about where we're headed. And I'm sure the talks that you heard the last few days, I know Professor Katerina Giotoplo was one of the speakers, and Professor Pastana, and they talked about some of that stuff that I just mentioned up there, among others. I don't want to be just mentioning those two. I know several of the speakers that spoke in the last few days. I certainly know a couple of the ones coming up in the next 2 days. So the talks over the past few days and those to be presented tomorrow and on Friday, and Professor Hashas has done a lot of work in this nonlinear arena, will attest to that we have got that improvement. So I finally congratulate the organizers of this conference and wish all of you safe and happy days. And any questions? Thank you very much.
Thank you very much, Professor Idriss, for your presentation. It has been very helpful for us. We will now start the question and answer session. So I will read you the questions from the attendees. Jorge Chavez asks, what construction and design considerations were taken into account to prevent or mitigate the liquefaction trigger with blast upgrading?
I didn't quite understand some of the words. Let me increase the volume of my computer. Could you repeat that question, please?
What construction and design considerations were taken into account to prevent or mitigate the liquefaction trigger with blast upgrading?
I mean, the example I was talking about?
Yeah, about your example.
Oh, the blasting was to actually induce settlement, cause liquefaction in the soil, and induce settlements that results in densifying the soil. But what we did before any blasting was done was actually do blasting and then measure velocities, particle velocities, along various points away from a dam, so that no blast was anywhere close enough to cause any problems to the dam. Is that really what he's driving at?
Yeah, thank you.
Because the purpose was achieved by using blasting was to, because we couldn't go back to initially do SPT, or we couldn't really go do CPT. The material was just too had too much of the coarser material for this CPT to penetrate very effectively. So we had to rely on the SPT. And the Becker hammer is very variable. And the new procedure, which is called the instrumented Becker hammer, had not yet been invented. This was back in 2002 or 3 or something like that. I forget the exact date. So we had to rely on blasting at that depth. And okay.
Here is another question. Ronald Landa asks, Professor Idriss, thank you very much for your presentation. in regard to flow liquefaction, which is the most threatening soil between a clean, rounded sand and tailings you had to cope with?
Well, we know that tailings can really have a huge deformations. We saw that in Brazil. So we know, and those were non-plastic tailings. I forget the exact number for fines content. It was not very high. And there were coarse tailings and fine tailings as usual. And now we did see some major movements in the San Fernando Dam, which was sort of, it's a hydraulic fill. I mean, rounded is a very elusive term. Nothing is always, it's not like having pearl beads with you, are all nice and rounded. But there was a huge movement in the San Fernando upstream slide. It was 50, 60 meters traveling. In Alaska in 1964, there was a major subterranean landslide in the Port of Valdez, and the sand was fairly, it was not that, it was pretty clean sand. It was sand. It was not gravelly or coarse sand. It was sort of the medium to finer sand. And that moved hundreds of feet. So I don't see much distinction in terms of the ability to move, depending if there is the trigger and then the opportunity to move. I mean, if Brumadinho had something done to it a little differently, it may have collapsed, but it may not have moved. But it was it was already a liquid before it suffered the damage before the movement. So it just spurted out and moved. Does that answer your question?
Thank you. Yes, Professor. Thank you very much. So if anyone in the audience have any question?
Arturo. No, I mean, just more than a question, just a comment. I think as a panelist, but more as an attendee of the event, I hope everyone realizes the honor that we have today to see this presentation by Professor Idriss. He is an absolute legend on this field. He is the one that invented it all. He and Professor Sid came with this concept and basically developed the world that we have today in terms of the understanding of this. I just want to make sure that everyone is completely aware of the privilege that we have to watch this like this, live, and he going back and looking his career in the past, 60 years and explaining this step by step, the way that he developed all this. So I honestly feel privileged and honored to have presence and witness this presentation today. So just wanted to say thank you to Professor Idriss for spending the time with us to cover all this. And yeah, I definitely got excited for the rest of the night because not every day you get a legend like this telling you how they develop, what we do every single day today. So it was awesome. Thank you.
Thank you. Thank you very much. And I think the late Professor Sid and I started things, but a lot of absolutely marvelous people are continuing the work. So I'm very excited about the future.
Thank you very much, Professor. I think all of us here feel the same way.
Thank you. Thank you. It's my honor and pleasure. So
on behalf of the National University of Engineering in Lima, Peru, and GeoGroup Uni, we thank you for attending this Congress.
Thank you. Thank you for inviting me. And we did this in person a few years back, maybe about 10 years ago, I think, with Menendez, Menensis, yeah. I'm terrible with names.
Thank you very much.